My name is Brennan Doherty. I work directly with MyFab, and really my role is to travel across the country, just meeting with owners, engineers, design build contractors, and architects, educating them on siphonic drainage. What is siphonic drainage at its top level? When you were stealing gas from dad's car back in the day, we got that hose primed with fuel. We created a siphon effect. The fuel just keeps coming out. That's exactly what we're doing, except at the roof level. To give us kind of a video visual to understand what's going on, I want to start with this. The intent for siphonic drainage is that we want to fill these pipes 100% full of water. The natural height of the building creates a negative pressure, which pulls that water from the roof clean through the system. What we'll discuss today during our presentation is just the differences between siphonic drainage and traditional gravity drainage. That way you can understand what the benefits are, as well as just some of the things we do have to be aware of. Rain event ends, rain's going to dissipate, and that system is just going to clear itself the same as we have with gravity. The first major difference and advantage of a siphonic system is it allows you to use roughly half the diameter storm pipe. So where you're running an 8-inch gravity, it can be a 4-inch siphonic line. Why is that the case? Traditional gravity drainage requires 2/3 air mixing with 1/3 water in order to efficiently transport through that system. With a siphonic drain, we're actually going to introduce a baffle plate over top, which is going to eliminate air from entering that pipework. Because we don't have the air in there, that's how we're getting that half diameter. The second major advantage is pipe in a siphonic system runs dead level flat. There's no installed slope or pitch whatsoever. Similar to a fire protection system, the routing as well as the demand up at that roof drain are fed into a balancing program that dictate back to us what those diameters need to be so we have an efficient system. I need 30 feet of 3-inch pipe here, 40 feet of 2-inch pipe, so on and so forth. If I was explaining this to a high schooler, my vertical is my energy gain, my horizontal and my fittings are going to be my energy loss. That's really it at its most basic level. The biggest issue with gravity is we're dictated by pitch. We can only go so far with that pipework before we get into livable space, at which point we have to drop vertical leaders all throughout our design. The intent for siphonic drainage is we want to collect everything up at this top roof level, routing it to one vertical drop, where we can then also define where we want our civil connection to be, rather than gravity dictating it for us. Gravity drains clog. Okay, it is inevitable. You can do your regular preventative maintenance. However, we know that goes by the wayside, and this is a very real situation. Scuppers do not get away from this either. What about siphonic drains and debris? In the video we're about to share with you right now, what we've done is taken 3 giant garbage cans full of wet pine needles, and we've thrown them in here about to simulate a flash storm. The first thing I want you to notice is there's no debris guard or dome over a siphonic drain. What happens with traditional gravity is what we saw in our last pictures, and we know to be true. The leaf and debris ends up getting pulled towards that drain and collecting on the side of that dome, meaning that water level has to rise in order to overcome that leaf and debris to exit the system. So we start seeing our wet spots, our leaks, and ultimately our roof drain failures. With a siphonic system, you'll see here after about a minute's time, when this water level's gone back down, there's no more leaf or debris left on this roof. It is pulled clean through, almost like a shop vac. And it wasn't a start and stop video, it wasn't sped up. That's just real time. All of that leaf and debris is pulled clean through the system. A video is great, but even more impactful, we have this system installed on over 1,000 plus Walmarts all across the US. So we know in every single climate, this is tried and true. As well, siphonic drainage has been over in Europe since the 1980s. So the ability for it to self-scour is widely known. This is not a secret. The biggest misconception I hear, though, traveling across the country is, we need to submerge the drain so it gets to siphonic. That's going to be more water weight. We're going to have to talk to structural. Logically, I can understand, but it could not be further from the truth. Reality is, it only takes about 1/4 inch to 1/2 inch of ponding in order to achieve that self-scouring velocity. So it's not much. What's happening is stage one, any light rainfall we have, a siphonic system is going to act just the same as a gravity. Even though that pipe is flat, water always seeks to find its own low point. If you go home today and pour your water bottle into a Glad container, the water doesn't go to one side or the other. It levels out the entirety of that container. Poke a hole in the bottom, water goes to that low point. Stage two, this is when we're going to have that siphonic action first start. So if any leaf, debris, plastic bag, it's going to get pulled clean through. And this is only 1/4 inch to 1/2 inch of ponding. Stage three is trying to get there. And stage four, we have complete submersion of the drain at this point. That pipe is 100% full of water. For a siphonic system, there is always going to be less ponding compared to a traditional gravity. It's about 3 to 4 times more efficient. And you can see at that overflow mark, that's exactly what metrics it's hitting. Now that we have kind of our basic building blocks, let's put it all together and see why it's delivering such a value. First off, that decision on the roof is affecting more than just our plumbing scope. It is affecting our civil scope as well, as we can visually see here, but let's unwrap it all. The elimination of these vertical downspouts, not only is that material cost, that's also install labor. The elimination of this internal excavation, which is within 5 feet of the outside of the building, so that's our responsibility. But we see on the outside, the elimination of these manholes, the elimination of this pipe work, which is large diameter because it's outside the building, plus the trench, the pipe, and the bury. But regardless of what side of the coin you're on, if we only have to route everything to one vertical drop, and this is not a complex system by any means, we can cut down on the calendar days, the coordination, and the potential conflict that could arise from these projects. Taking a look at some real life project examples and just really how you can get the most out of Siphonic. One, here's our list side by side, but high rise is another great example where we can see cost savings, anything over really 5 stories, right? Thought being that on most of our designs, we're having our risers on the outside of the building because sloping to the center doesn't make sense. We need more building height. And once we get to the bottom, we're gonna have to slope to get out to civil. So that's a poor design. With Siphonic, the intent is we grab everything up at this top roof level, route it to our ideal vertical, and then make that civil connection rather than needing to come all the way around the building to get that done. But at its most basic level, this design right here has 8 different vertical shafts for gravity storm. Going with a siphonic system, we were able to route everything to one vertical location. And in this scenario, we only had about 13 feet of siphonic pipe, at which point it reverts back to gravity and they're running gravity through their building like they have every day of their life. Advantage though, 7 less vertical, they no longer have to worry about coordinating. High rise example, right? Even though we have 4 drains, traditional gravity has them each routing by themselves, 136 foot. For Siphonic, we don't have to kill it at that roof level. We can take it all the way through that building and then break it once it finally gets outside. You're still going to have an overflow system. In this scenario, you can see they just ran in parallel, but we eliminated 3 different vertical shafts in this scenario. For a warehouse, more advantage. Instead of doing your traditional, where we're going to go ahead and go into the ground, make our gravity connections up front as well as the back. Civil will figure out how we collect it. We're going to route everything to the back of the store. That way, we don't even have the need for civil to come to the front of the building. Same idea, route it all the way to the east here. We can connect these two together. So instead of having two civil connections, we have the ability to connect both those runs and eliminate one connection to that building completely as well. This photo really doesn't do justice for how big the building is. Point of this example though, it's about a 36-foot tall building, 40-foot drop overall. We're able to run 850 feet dead level flat, no pitch, no slope whatsoever. So with gravity, you don't even have this available. You've got new things in your toolbox that aren't currently possible. And really to squeeze the lemon to understand what its maximum capability is, I want to share this project. In the original design, they found they were only having the civil pipe work come to this far west side just to connect to the storm system. There was no other need. So what they did on their design was, number one, they routed all of their primaries to the front of the building, eliminating the need to even go back there. But two, once it got to the front of the building, they actually dropped the siphonic portion inside of the building and ran it dead level flat in the ground. Reason and why. One, they eliminated the need for the civil to come over here, which is civil sized pipe and sloping. Plus, it needed to be at a 4-foot depth. Inside the building, we kept it small diameter pipe. We ran it dead level flat, and they kept it at 2 feet, saving on trenching costs. When they got here to exit the building, they went around the footer, and working with the civil team, they decided to keep it siphonic going outside of the building as well, where they then finally broke back to gravity and discharged into the civil. Outside of just Walmart, which we stated earlier, we have a number of firms that are working with us across the US. Point of this slide being, you're not a guinea pig and we're not a high school science fair project. Kind of our just little, who does it affect? Where does it have the most value? We've covered a lot of this today. I have a little flyer I can send you after this, but as you can see, it really is helping everybody in the whole job team. Now, kind of our final portion. What drain options do you have? What are your limitations that you have to be aware of where it's just not going to be a good fit for your design? First, really not a whole lot of drain options at its base. On the left, you got your typical TPO membrane. Membrane's going to go in there, clamp down with the friction force, same as we do with gravity. Here, we have a gutter style drain. We use this a lot of times on like stadiums or larger drains where it's maybe a one slope drain going to a gutter. What it allows them to do is keep everything flat, hug the corners, and get to your ideal discharge location. Giving us just some kind of larger warehouses and picture visuals. Concept is what we keep talking about, to run that pipe dead level flat, eliminate any of that site disturbance we have, having that groundwork move. Give us an example, and on the next slide too, we do have costs from an owner. But the original gravity scheme for this one is what we see on majority of our designs, right? It goes to a gravity drain where it's then gonna hug a column, go all the way down to the ground. In the ground level, everything is trenched out till it gets to the outside of the building. We get to the outside, the civil connection is made, and then everything collects on the outside. With a siphonic solution running dead level flat, we're able to first collect pairs of those drains up at the roof level. So instead of having all these vertical drops, we could collect them up there and then finally eliminate all of that internal pipe work, all of that internal trenching to eliminate the site disturbance and eliminate the number of civil connections. The developer on this one said they saved $1.7 million. Keep in mind, again, this was a 1.1 million square foot warehouse, so a tremendous impact and a little bit different of a design with those internal roof drains. Other option we have for siphonic drains is putting one in a parking sump. We also offer trench drains, so it's a standard grate. Working with Amazon on one of their projects down in Florida, the benefit for them here was we could collect more drains together, which means we had less vertical shafts. Having a smaller diameter pipe means it was a smaller coring through that sidewall. And finally, on this particular project, they used a cupolex, which is a type of rainwater collection system. Siphonic gave them the ability to find where they wanted that discharge to be, rather than gravity dictating where they would need to have this in the building. We also have stainless steel ADA proof ones, so it's walkable. Ballast guard, if you're doing a paver style roof, we can just throw something over it to protect it, but it will work in those situations. A trench drain as well. So Siphonic is just in the bottom of that trench. You have trench going there as you normally would, half diameter pipe. And we did use this with Costco down in Mexico, where they threw a soccer field and basketball courts on top of one of their buildings. Last kind of little cheat sheet, what you want to be aware of where this system is not going to have an effect. First off, the projects we're really looking at are anything with an internal storm system. Rules we need to be aware of. Number one, all of the drains connected need to be on the same roof level. Reason being, if they weren't, we might be getting the chance of air and grass at this lower level. Not the end of the world. You'll have two separate siphonic systems. You can break them back to gravity and connect them together. Or if you have the ability to drain this upper roof gravity to this lower roof, you can just drain that lower roof siphonic. Rule 2, we have to make sure every drain on that siphonic system has a minimum design of 23 gallons per minute. What that basically means is we can't have any area drains or planar drains be connected, as they just would never receive enough rainfall rate to get to that self-scouring velocity. Your minimum does take into account your rainfall rate. So depending on where that project is, this is a different metric. But just as your rule of thumb, we generally say about 750 square feet. On the maximum side, our 6-inch drain can handle up to 57,000 square feet. So you're really going to get to your comfort level with pitch and slope of that roof before you're going to hit the limitation of that drain. Second thing we want to be aware of, for a siphonic system, we are always going to break back to gravity at point of discharge. It's 2 rules to accomplish this. We're going to increase that pipe diameter back to that IPC or UPC flow chart. And number 2, we're going to reintroduce atmosphere. Number of ways to do it. You could do it in the vertical. We're just going to go right back to the roof or out a sidewall. You could do it in the civil. We're always going to have a manhole. We just use a slotted cover instead of a solid cover. Or the third option, what we see most commonly is the engineer puts an area drain 5 feet outside of the building. That allows that atmosphere to come back in. And we do ideally want it to be as close to that siphonic break as possible. However, there's nothing within the standard that states a maximum distance. So this could in theory be, 50 feet, 25 feet away, but we want to make sure we're reintroducing atmosphere. And then 3, there are additional bracing requirements. They're very easy to suffice. 3 and 4, we're doing for gravity already anyway. Just support it in the horizontal, brace it in the vertical. 1 and 2 are new. 1 is we need to make sure the pipe is braced at every change of direction. So Ys, we have 3 points of brace. 90s, we have 2. And then sway bracing every 30 feet in the horizontal. We generally already have the clevis hangers there. We're just going to add stainless steel aircraft hanger cable here to make sure it's taut. The purpose is to make sure that pipe is rigid. It is not moving longitudinally or laterally. If you guys do have a design, 2 things we need to make sure we're aware of. All the drains connected are on the same roof level, and we're hitting that 750 square foot minimum. What we need on our end is to understand the routing, both vertical as well as horizontal. And then our team take it, prepare a model for you. It'll have the install blueprints as well. So that way the engineer can go ahead and throw it right in a set, and that contractor can see exactly what has to be installed.